Ok, immagino siamo d'accordo tutti che si registra. Ok, iniziamo. Questa è la registrazione, prima parte della lezione di 9 dicembre. Io prima di tutto vorrei chiedere se avete qualche domanda collegata con la lezione, forse una parte della lezione è già dimenticata, ma vi ricordo che avevamo queste quantità alla media che era la speranza. Let me switch to English, of course. Expectation. The expectation is defined, has very simple, nice properties. Expectation of sum of function is two functions is sum of the two expectations, and we had some other rules. Then we have defined for two or more than two random variables the property that they are independent, and this independence was connected on one hand with probability that two random variables x and y had respectively values ij, and we wanted this probability to be the product of two probabilities, respectively x to be I and probability epsilon to be j. We defined a covariance of two or up to random variables, and then we defined the variance, and we explained several nice properties of random variables and their variance, especially very important. One very important property is the property that when we have x and y independent variables, random variables, of course, would explain this property that they are independent with a product of probabilities, but we can simply use the notion of covariance of x and y, and we said that the independence means practically that it's the covariance between these two guys is 0, and we had very important lemma. Remember that variance of sum of x plus y, when they are independent, was equal to the variance of x plus variance of y. This property is independent because in order to finish and complete our study of the basic facts of probabilities, probability densities, we need the law of big numbers, and to explain this law of big numbers, we need especially this important property. Let us call this important property 1, and then we had, remember the definition of the variance. This was covariance of xx, and this was expectation of x squared minus expectation of x to the power 2. So we had, due to this quadratic behavior of our variance, we had also another important property. Probably here you cannot see. Let me clean the part above. And here I shall put the last property that is needed for the law of big numbers. Let me see if it is working. Oh, it shall be not very wet. For example, if you take variance of constant times x, what happens? Thanks to the fact that constant in the expectation goes out with the same power, C, here for the variance we have C squared, the variance of X. Let us compare this important property and recall you that if you have the expectation of Cx, this is simply C, the expectation of X. We shall call these properties here, how you can see these properties too. And after this preparation, we can recall two important inequalities that are needed to practically to evaluate. Yes, but before going and cleaning the whiteboard, let me ask you if these reminders remain recalling the last things we did. Is it clear for you? Do you have some question?
For me, it's clear.
Okay, let us see the other participants if they agree.
Clear.
Yes,
Professore, scusi, una precisazione soltanto. C quadro davanti alla varianza quando porto fuori la costante è dovuto al fatto che posso vedere la varianza come la covarianza di 2 volte x e quindi avrei...
Exactly.
C.
Exactly. This is very important thing. We can generalize and take covariance of this here. We can put one constant. Here we shall put another constant. And each of the constants go in front because this is so-called bilinear form, and with respect to each of variables is linear. Therefore, C goes out like C to the power 1. So if I have here only C, goes out as C. If I have here D, D goes out like D. Therefore, if I have here CD, they will go in front like CD. And if we repeat CC, this will become C to the power 2. Thank you for this observation. This is really very important property. And this is nice observation. Other your remarks or some questions, observations? Okay. If not, let us recall you that what we have to evaluate is connected with, we shall call this law 1, law 2. Now I need to clean everything in order to go further. If at some point, because it may happen that registration is stopped by itself, and who knows, please to tell me if this red bow in the left upper corner is always registering, recording, because in some cases the students told me that occasionally this may disappear, so let us be careful. Okay, now let us make it a little bit better. Okay, so which are the events that we want to evaluate? What kind of probabilities we want to study? If we have one random variable x, the fact that this random variable is bigger than a, of course, this is one of typical events that has to be measured, evaluated by means of the probability. And this is done by using Markov inequality. And we said that when we have one random variable, this probability is bounded by the expectation of x divided by a. So this is very simple property. The last time, did we discuss the proof? Do you remember?
No, we didn't.
Okay, so since this is very important Markov inequality, let us make short proof. Of course, everything is connected. Here you can imagine that we have capital P because this is probability of this event. We know that probability big P for the event x bigger than a, this is very simple. So we have to take our integral. We take our probability density, dx, and we integrate for the case when, let us assume that x has interval where this random variable is studied, that is 0, infinity. We can take minus infinity, plus infinity, but for simplicity, I took 0, infinity. So this probability of this event means that we have to take simply the integral from a to infinity. What will happen if I take integral from 0 to infinity? Let us for the moment ask this question. If p is random variable, integral from 0 to infinity of px dx shall be exactly equal to what you predict. What do you think?
1.
If I take this integral from 0?
1.
Shall be exactly 1, because this is the definition of probability density. When we integrate over whole interval E, this probability is 1. What will happen if instead of 0 I take 1? What is bigger? Integral from 1 to infinity or integral from 0 to infinity? Of course, integral from 1 to infinity is a little bit smaller because we take smaller domain of integration. Our function p is, for example, if our function p, x is here, we said x varies from 0 to infinity. And if we suppose that our function is like this, what is the meaning of integral from 0 to infinity? This means that we take the whole area below the graphic of the function p. If instead of integral from 0 I take integral from a, of course I shall have smaller domain and the area shall be smaller and smaller. For this, this is something that we expect that when a is very big shall be very small. But how small? This actually is given by Markov inequality. So this is on the left-hand side. How we estimate integral from a to infinity px dx. In order to get the expectation, we know that the expectation is integral in which here I have x. So artificially, I put this factor x, and if I put this factor x in order to have the same probability, I have to divide by x. So what we shall do? We have to estimate as it is shown by Markov. So when x is bigger than a, what we can say about 1 over x and 1 over a? Who is bigger? Which term is bigger? X is bigger than a. Then 1 over x is
Smaller than 1 over a.
So we have this inequality. So I replace denominator by a, and I can write integral from a to infinity x times, x over a. Now we know that a is a constant, so 1 over a can be put in front. So this is 1 over a integral from a to infinity x px dx. And we're almost done. Why? Because here the integral is from a to infinity. If I enlarge the domain of integration, going to the whole available interval from 0 to infinity, of course, we shall have bigger 1 over a integral from 0 to infinity x px dx. And as you know very well, this integral here is the expectation of our random variable. So we get expectation of our random variable divided by a. And this finishes the proof. So what we have done, multiplied and divided artificially by the weight x. Then we realized that this here is the other part. We realized 1 over x is smaller than 1 over a, so we estimate 1 over x from above by a constant. We put the constant in front, and then we simply enlarged a little bit the interval and get this integral that gives the expectation. So the Markov inequality is established. It shows that when a goes to infinity, since this quantity is fixed, the speed with which your probability goes to infinity is 1 over a. I would say that a typical graphic is not this one, but if we go to infinity, I would expect that my function p goes very rapidly to 0, because otherwise our integral from 0 to infinity of px is not bounded, shall be not 1, shall be something undefined. Therefore, the more correct graphic of our function p is positive, but as you can see, when x goes to infinity, probability density px goes to 0, and when we take even x is bigger than a, probability that x is bigger than a, this is so-called tail. The coda, the remainder is very small. How small? It is evaluated by Markov inequality. Okay, you can take a look on the proof and ask me if some point in the proof is not clear, if you need further details. Okay, if this Markov inequality is clear, then we can say what is the purpose of our lecture today. Of course, we shall use Markov inequality, but finally, our purpose is the following. We take many random variables. Since the processes in the real life are very complicated, the types, for example, of cells, the types of genes are very, very different. We can consider a large, big number of random variables. So the classical situation is the following. we consider this is the law of big numbers. What does it mean? We have many x1, x2, and so on, xn random variables, but we have to specify that they're independent. Independent random variables. Sometimes in Italian this is Legge di grandi numeri, but in the literature is central limiting theorem. Let us put also this notion, central limiting theorem. Of course, there are different types, but this is actually the idea to consider many random variables, but independent. Moreover, we assume that they have fixed variance. Therefore, we take variance of all these xj is fixed mu. Expectation can vary, but we can take the variance. Sorry, mu is not, after this we shall use the variance, the expectation of all this for the moment is fixed. In general, it is more natural to assume that this expectation have limit when j goes to infinity. But for simplicity to understand the situation, we assume that expectations are the same. And then we consider the following event. x1 plus x2 plus xn divided by n minus mu. This absolute value to be bigger than epsilon. We can say that this is again kind of a back tail. What we expect is that the mean value of these n random variables shall be very close to mu. So our purpose shall be to evaluate the probability that our statistical data will give a result that is the mean value of the result is outside the interval of radius epsilon around mu. So what we have geometrically, we have this mu, and then we take the interval mu minus epsilon, mu plus epsilon. So what may happen? If I take the mean value, my mean value can be inside this interval, therefore we have a good case, but it may be the mean value can be outside. So I start to count how many times my statistical mean values is outside this interval. And actually, the number of these cases is very small. The law of big numbers practically says that this goes to 0 as n goes to infinity, but actually we shall see that this is smaller than constant divided by n. Therefore, again, we shall have similar property that bad cases, the tail, that is the cases when our data are outside this interval, that can be chosen. We can choose, for example, we want to see our result shall be with, if we expect mu to be 5, we can say we need the result to be precise up to 1%. Therefore, we have to take epsilon to be 1/100 multiplied by this number mu. And if we have 5 divided by 100, this means epsilon is 1/20. Depends on the concrete cases when we need precision, we need error that is very small. We need to be sure that the error of bad statistical data is really very small. So we choose this epsilon to be very small, and then we fix this epsilon and we take sufficiently large number of experiments. If this number is sufficiently large, if we repeat our experiments and if they are independent between each other, then the strange rare cases outside this interval are really very small. They, for fixed epsilon, they decay like 1/n. This is the law of the big numbers, and we shall try to clarify how simply this can be deduced using Markov inequality and one more inequality that I shall explain you after a while. But first of all, I want to give the idea of this important rule that shows that if we have independent random variables, and if we make the experiments with these random variables for big number of random variables and take the mean values, then this probability, practically our mean value with epsilon probability is close to mu at distance epsilon. Therefore, almost all values shall be close to mu. And this practically is justification that if we repeat many times, for example, experiment with dices, probability to have 1 shall be 1/6, but we have to make many attempts, because with 2-3 attempts we may have really strange results, even with 6 attempts. Okay, so this is the idea. And before going further with explanation how this can be proved, let me ask you if the main idea is understood at this point, or if you have some doubts, some questions. Actually, our first step in our approach to law of big numbers is to consider the case of one random variable and measure this probability, and then to try to go further and go to the case of n independent random variables. Okay, so I shall clean again the whiteboard. And we can turn okay. So the preparation for the law of big numbers starts with the following simple lemma. X is a random variable of expectation A of X we set is fixed, and we can also put the variance of X to be sigma square. So what we need in this case is to specify that our random variable has interval 0 infinity, and here we have, as usual, the small function p of x probability density that is defined here, and such that integral from 0 to infinity, let us recall this, from 0 to infinity of p x dx is 1. The function p is non-negative, smaller than 1, and the total integral is normalized in this way. So we want to estimate probability. Let us put big P. Probability that x minus mu, we set one random variable, is bigger than epsilon. Of course, if you have x a real number, mu real number, positive, this inequality is equivalent to say probability of x minus mu square is bigger than epsilon square. And we have to estimate this probability. Actually, this shall be done in the next lemma. That is known as something that is difficult for Italians to pronounce, because this is again a Russian mathematician, Chebyshev inequality. What is saying our Chebyshev inequality? It measures this probability. We shall see probability that x minus the expectation is bigger than epsilon. This shall be estimated from above by the variance of our x, therefore sigma square, divided by epsilon. We shall see, I think, epsilon square. We shall see from the proof. So, if we have the case of one random variable, and if we fix this number epsilon, of course you can, instead of epsilon, you can put a, and this shall be a square. You can put any letter, but here epsilon is positive. This is Chebyshev inequality, and as you can see, this inequality is very well connected with the law of big numbers, because this is practically the case of one random variables. After this, we shall see that when we have the mean value, we can compute relatively easy the variance of the mean value of n random variables. But here the situation is simple. We have only one random variable, and for this random variable, we are planning to prove this property. So, how we can proceed? Of course, the key point in order to prove this lemma is to use the relation above. We can say that here I don't need to put absolute value. So I simply take, these are real numbers. So when you take a real number to the power 2 or absolute value of a real number to the power 2, they are absolutely equal. But this now for me becomes function of my random variable. And we know something for this function of random variable. What we know, let us write proof. Again, proof is quite simple. I shall write for you the inequality that we established a few minutes ago. Therefore, we have. So I shall give the idea of the proof and then we shall make a break, because imagine that one moment, then I made a mistake. Wednesday was completely, we decided that Wednesday you shall be at home, is it? While Tuesday was the day where, no. What was our, I think today I have to come.
Yes, it was.
Yes. So I didn't make a mistake. Okay. In sense, no problem, because in any case, the lecture is doing well and you actively participate. This is the most important. So let us remind you the Markov inequality. Of course, if I write here bigger or equal, this is not a problem, because when you consider integral, the value of the function in one point shall not change the volume of your function. Therefore, you have the same inequality with epsilon bigger or equal or epsilon bigger. So what gives Markov inequality? This is smaller than expectation of epsilon divided by A. This is Markov. Easy to pronounce probably. And now we are to the complicated Chebyshev case. So what I shall do? I simply shall call this shall be my epsilon and this shall be my A. Because again, function of random variable is again a random variable, and we know how to compute the expectation of function of random variable. So this shall be exactly equal the probability that x minus mu to the power 2 is bigger than epsilon. If you want to write bigger or equal, this is all the same. Epsilon squared. This shall be smaller or equal than the expectation of epsilon. So this is the expectation of x minus mu squared divided by A. But my A is epsilon squared. So we apply Markov inequality. And now we can do the calculation of this expectation. This expectation is practically the variance of our x, y, because you have here expectation. Now I start to take the square of these two quantities and I get x squared minus 2 mu x minus mu squared divided by epsilon squared. This is plus. So we have that expectation of sum of random variables is sum of expectations. So we get, I don't know if here I have a little bit space because I see my presentation in very small rectangle. Can you see, can I write here or it's better to write above?
Maybe it's better above.
Okay, then I shall write bigger. But remember that at this point we applied Markov. This is Markov inequality. And now I shall clean the Markov inequality above. And we can finish the proof. Because first we have first guy is a x squared. This is too high or you see?
It's okay.
Okay. Denominator is always epsilon squared. Remember here denominator in order to avoid to put epsilon squared. Then we have minus expectation of mu 2 times mu x. But we said that constant time x, the constant in expectation goes out. So we have minus 2 mu, the expectation of x, plus, then we have mu squared. Expectation of 1 was this guy, because we have a total integral from 0 to infinity, and then we have identically 1. So we have mu squared. But what is ax? By definition, mu is the expectation of x. So here we have minus 2 times mu squared plus mu squared. This will give us a of x squared minus mu squared. Minus 2 mu squared plus mu squared gives minus mu squared divided by epsilon squared. If we recall the fact that mu is the expectation, we have expectation of x squared minus expectation of x to the power 2. The numerator is exactly the variance, because this was our definition of the variance of x divided by epsilon squared. And we said from the very beginning that sigma squared is the variance of our random variable x. So this completes the Chebyshev inequality. The only thing I have to add here, sigma squared is the variance of x. This is important to clarify what is written in numerator. So Chebyshev inequality is inequality that connects this difference, the fact that we have kind of deviation from the main expectation, and probability to be far away from the expectation is really depending on the variance. Smaller variance you have, smaller error you have, smaller probability for bad event you have. And this is not only idea, but also the complete proof of Chebyshev inequality. So let me ask you if the proof is clear, if you have some observations. Actually, inside the proof, it is important that we use this relation. This is also very important. And actually, that's why I skipped to start with this guy, because this guy is equal to this guy. So to save some space, I started directly with the squares in order to arrive more rapidly at the end to the variance of the random variable x.
I have a question.
Please.
When we say that there is x squared minus 2 mu x.
Yes.
Why in the following passage I substitute x with the expectation of x? You wrote minus 2 mu expectation of x.
Look here. We have expectation of 3 random variables. So, the first expectation is this one. The second expectation is, if I am more precise, I should write here minus expectation of 2 mu x. And then I shall have plus mu expectation of mu square. This is due to the rules of expectation. Expectation is additive, so when you have sum of random variables, you take the sum of expectation. Here we can, your question is correct with this term or with this term?
With the one with minus, so
yes.
Yes.
Have in mind that under expectation we have random variable big X, and we have a factor 2 mu. Mu is a real number, therefore I can take 2 mu outside. So if I take 2 mu outside, I shall have minus 2 mu, because this is a real number, and then I have a of x. So I kept my notations. Expectation of this guy, since this is a constant, but this is a random variable, I put the constant in front, and inside remains expectation of x. But to this end, we can recall us that this guy is exactly mu. So this, by definition, we have specified that expectation of x is mu. So probably here I should write very clearly before Chebyshev lemma to write that expectation of x, this is important assumption, is exactly mu. So mu on one hand is a real number, but also has the meaning of the expectation. What kind of, how is defined this expectation? This is equal integral over our interval of small x, small p of x dx, where p is the probability density. Therefore, I know that the whole integral is mu, and I simply put the constant in front, and I have the expectation. But I know that this expectation is mu, so I put equal to mu, the expectation, substitute with mu, and this will become minus 2 mu times mu minus 2 mu squared.
It's clear, thank you.
Okay, okay. Thank you for your question. Please to ask any moment. By the way, how we computed this? This we said that what is the definition of the expectation of x to some power kappa? Let us remind. Can you see here?
Yes.
Yes.
This is by definition integral over our interval x to the power kappa p px dx. So when kappa is 2, we have expectation of x squared. This is the precise definition with probability density. If kappa is 1, we have the expectation of x. But look, here you have 1. 1 is x to the power 0. If we take x to the power 0, we get, when kappa is 0, integral of px, and this is 1. That's why here I put 1 for the expectation of the constant of 1. Took mu square in front, expectation of 1 is identically 1. This is to remind you how we compute expectation of powers of or functions of random variable. Okay, then some other questions. My proposition is to have now stop the recording and to have 5-10 minutes break, and then we shall have a short part where a large number theorem shall be presented in very simple situation. We shall see that the proof is quite simple, and we shall have complete picture of this small introductory part in the probability. But we shall, after the next week, have some speak about another applications connected with statistics, data statistical evaluations. Okay, let me stop to record.